Okay, so welcome to everybody. So this is the second session of the workshop on interactive adaptive learning. As the previous session, we are going to have one invited talk and two regular papers. You may see on the bottom of the screen, there is a box for Q&A, so for question and answer. So you can raise question during the talk, and everyone may vote to give a preference for the first question, for example. So don't hesitate to use this Q&A box during the talk, and we are going to give the turn of speech for this question after. So I'm very happy to welcome IJCNN for the invited talk with the title How to Measure Uncertainty in Uncertainty Sampling for Active Learning. I share in the box the paper, the title of the paper which is concerned by this talk, so you can see this title and how to find this paper. So welcome, IJCNN. I'm very happy to welcome you, and I give you the turn of speech. So at first, we are going to see the video of your talk, and then we are going to have time for questions. So Daniel, if you can start the video, please.
All right. So welcome everyone to my presentation on how to measure uncertainty in uncertainty sampling for active learning. Thanks a lot to the organizers for inviting me. It's a pleasure to give a presentation on the occasion of this workshop on interactive and adaptive machine learning. So the topic I'm going to address today is one of the topics that is highlighted for this workshop, namely active learning, which is, yes, one of the relevant, let's say, topics in this realm of interactive and adaptive learning. More specifically, I will speak about uncertainty sampling, which, as many of you will know, is one of the best known and most commonly applied methods for active learning. It's a specific type of what is called pool-based active learning. And yes, as one more restriction, today I will mainly speak about binary classification. So let's say the simplest case of uncertainty sampling or machine learning problem that you may apply active learning to. So my focus will be on uncertainty, and how to measure uncertainty, as I already said. And this is why I'm specifically looking at uncertainty sampling here. So just as a very brief reminder, again, most of you will know quite well, active learning or uncertainty sampling essentially works as follows. So here we consider, as I said, a binary classification problem. You may, for example, be interested in learning a classifier that predicts whether or not a certain patient suffers from a certain disease. A patient here, for example, could be represented by an X-ray image or a numerical representation of that image, a point in a high-dimensional Euclidean space. For illustration here, just a two-dimensional space. So, and then we can assume that we are given some labeled training data points and a pool of yet unlabeled data points. So these are shown here in gray. So this is our pool. So given the current training data, the labeled part of the data, we can fit a model, for example, just a simple linear discrimination function like the one here. And then the idea of active learning is that the learner has the ability to actively query a next training example to learn from, instead of choosing one at random. And in uncertainty sampling, this is done by picking that data point for which the current predictor is most uncertain. So what we assume here is that we basically have a probabilistic classifier, or at least a classifier that is able to quantify its uncertainty in a prediction. If the classifier is a linear classifier, then, for instance, it's natural to have a measure that decreases with the distance from the decision boundary. So typically those instances closest to the decision boundary are assigned the highest degree of uncertainty. So these could be, for example, be probabilities of the positive class. And then the closer the probability to 0.5, the higher the uncertainty of the predictor. So the one with the highest uncertainty, which might be this instance here, is selected, it's queried. The oracle, whoever that might be, a user or so, a medical doctor in our example, is providing the label, might be negative in this case, then the model is adapted. We have a new piece of training information, the model is adapted. For example, shifting the decision boundary from the solid line here to the dashed line, and then the whole process iterates. Of course, you can do the same thing with other base learners, like, for example, a simple Parson window. This data point here might be specifically uncertain because within its neighborhood, half of the cases are positive, half of the cases are negative. So if you estimate probability in terms of relative frequency, you will have a very high degree of uncertainty here. Indeed, what we assume most of the time is that our classifier is a probabilistic classifier in the sense that it delivers as a prediction a probability distribution over the set of classes, a conditional probability distribution given the query instance X. Here, this parameter vector theta is supposed to identify the classifier. So imagine we are working with a parameterized model class or hypothesis space. The theta here identifies the predictor. And what you see here is a list of commonly applied measures to quantify the uncertainty. This is an important point because if you want to apply uncertainty sampling, you need a measure of uncertainty. How uncertain is the prediction? The most commonly used measure probably is the Shannon entropy. It's given by this expression here: the higher the entropy, the higher the uncertainty. But other measures can be used as well. So, for example, the confidence. What is the probability of the most probable class? The higher, the better, the more confident you are. The lower, the more uncertain you are. Or what is the difference between the probability of the most probable and the probability of the second most probable class, and things like this. So there are various measures you can choose from. In the case of binary classification, they essentially all coincide, but in more general cases, they may also lead to different selections. All right, so the main point of my presentation today is, let's say, the idea that it might be interesting in the context of active learning, specifically uncertainty sampling, to go beyond standard probability measures, to represent predictions and beyond standard measures like entropy and so on to quantify uncertainty. And in this regard, what is specifically interesting is the idea to distinguish between different types of uncertainty. And this is a topic that in general attracted quite some interest in the recent machine learning literature, especially also in the deep learning community. One specifically important distinction seems to be between what is often called aleatoric and epistemic uncertainty in the literature. So intuitively, what do we mean by aleatoric and epistemic uncertainty? So aleatoric uncertainty is, so to say, uncertainty that is due to inherent randomness, so stochasticity. So the prototypical example is coin flipping. You flip a coin, there are two possible outcomes, head or tails, and you don't know. And then if you have to assign a probability distribution, assuming that the coin is fair, you will assign 1/2 probability to both possible outcomes. So as another example, consider the question, what is the meaning of the word Kichwa in Swahili? Yeah? So the word either means head or tail, this is what I can tell you, but you don't know which of the two is true. So you are probably as uncertain as in the coin flipping example, and if you have to assign a probability, you may also again assign probability 1/2, referring, I don't know, to the principle of insufficient reason or whatever, or maximum entropy. But the reason, this is important, the reason for the uncertainty is completely different. Yeah, here you are not uncertain because anything is random. No, nothing is random. You are simply uncertain because you don't know. Yeah? Due to a lack of knowledge that you could potentially get rid of. And this is important to note. And this distinction, it was already highlighted by the famous Ronald Fisher, a famous statistician, who said that not knowing the chance of mutually exclusive events and knowing the chance to be equal, like in the case of coin flipping, are two quite different states of knowledge, yeah, which ought to be distinguished, and the distinction of which could be useful at least sometimes. And our claim is that this distinction might also be relevant within machine learning, and in particular, it might be useful for active learning and uncertainty sampling. So where does epistemic and aleatoric uncertainty come into play in the realm of machine learning? When you learn a model and you use it to make predictions, there is always aleatoric uncertainty, simply because we basically never assume the dependency between instances and labels, inputs and outputs, x's and y's. We never assume that dependency to be deterministic. We always assume that the dependency is stochastic. Yeah, classes may overlap, etc. So you will never be able to learn a model that has a 100% accuracy and never makes a mistake. So even if you know the optimal predictor, let's say the base classifier, there will be some uncertainty left. And this is of aleatoric nature due to inherent randomness or stochasticity. But there is also uncertainty regarding the, let's say, optimal model itself. And this is due to a lack of knowledge, which in this context might be caused by, for example, a lack of data. Here's a simple example on the left. If you have to make a prediction for this, let's say, new patient here, you might be uncertain. And the reason for the uncertainty is mostly of epistemic nature. There is only little data you have seen so far. So you really don't know where is the decision boundary, whether this is a positive or a negative case. Here you are also uncertain on the right, but the reason is different. Here, let's say the uncertainty in a sense is confirmed uncertainty. Yeah? You have seen so many data points that you can be quite sure that this data point here, this new query, is lying in a region where the two classes are completely overlapping. Yeah? So here we have a situation of high aleatoric uncertainty. One important observation is that the say degree of epistemic uncertainty does not only depend on the amount of data you have seen so far, but also on the assumptions you start with. You start your learning process with, in particular, the let's say inductive bias, the assumption you make on the hypothesis space. Roughly speaking, the stronger that these assumptions, so the more restricted your hypothesis space, the more the data is telling you, yeah, and the more effectively you can learn. For example, here, if you make a relatively strong assumption that the classes, for instance, can be separated linearly, then even if you have seen only a few data points, you might be relatively certain that this one here is red on the positive side. Whereas if you weaken your model assumptions and you also allow, for example, to fit quadratic discriminant functions or nonlinear discriminant functions, then you might again be more uncertain, yeah, because there are some hypotheses in your space consistent with your data that would predict positive here, others that predict negative, yeah. So here the epistemic uncertainty is higher. So it does not only depend on the data, on the amount of data, training data, but also on the assumptions you start with. And actually, yeah, epistemic uncertainty depends on the interplay between the two sources of information. Okay, so in the context of active learning and in particular uncertainty sampling, one may argue that epistemic uncertainty actually could be the more relevant type of uncertainty, and more relevant in particular than aleatoric uncertainty. Yeah. So the conjecture, so to say, is that a learner's predictive uncertainty due to not knowing the epistemic part should be more relevant than its uncertainty due to confirmed randomness. And in particular, this should be the case because the former, the not knowing, could potentially get rid of, yeah, can potentially be reduced, for example, by observing new data points. Whereas the latter, by definition, actually cannot be reduced. So it doesn't make sense, for example, for an active learner to always query in a region, yeah, as we have seen here, in a region where the probability is indeed 1/2, 1/2, but you know it's 1/2, 1/2, and it won't get better even by querying new data points. Yeah. Okay, and this actually motivates what we have called epistemic uncertainty sampling, by which we simply mean uncertainty sampling where the uncertainty is quantified in terms of epistemic uncertainty and not total uncertainty as is done in standard uncertainty sampling, where, for example, you use the entropy measure, which in a sense is a measure of total uncertainty, capturing both types of uncertainty simultaneously. So this idea is not completely new. So, for example, a couple of years ago, there has been an interesting publication by Sharma and Bilgic, in which they make a similar distinction, not exactly the same, but similar, and they speak about uncertainty, which is called by conflicting evidence and so-called insufficient evidence. We later on in the experiments, we also compare to their method, at least in those cases where it's applicable. And yeah, what the implementation of this idea of epistemic uncertainty obviously requires is a quantification of the amount of epistemic and also aleatoric uncertainty. That means a quantitative measure of epistemic uncertainty. This is what I would like to elaborate on a little bit. So I don't have so much time to explain everything in detail. This would really actually require a more lengthy discussion. By the way, just as a side remark, allow me to make some advertisement for our tutorial, our ECML PKDD tutorial that will take place on Friday, connected to a workshop on this topic of uncertainty in machine learning. And there I will speak about these things also in more detail. So we have been tackling this problem recently more generally, independently of applications to active learning, the question of how to quantify epistemic uncertainty. Other people also did that. For example, as I said, in the field of deep learning, people started to also work on this. Here we used a quantification that we have recently been developed actually for another purpose, but it's exactly what we need, a quantification of epistemic uncertainty. And our point of departure is, let's say, to use more general measures to represent uncertain predictions, measures that are more generally than probability measures, because probability measures, in a sense, they are in a sense of limited expressivity and arguably not really suitable to represent a lack of knowledge, and this is mainly because they are additive. and therefore self-dual, which means that the probability of an event A is always 1 minus the complement of the probability of that event, and the total probability mass, so to say, is always 1. It's normalized. So you always, in a sense, represent the same amount of informedness, if you want. We are working with sub-additive measures that you may call plausibility measures. This is a term that is commonly used in the literature. These measures are not constrained by this property. The sum of degrees of plausibility degrees is not necessarily equal to 1. It's greater equal 1, and in our case, for example, we may assign degrees to the positive and negative class that are both between 0 and 1, but the sum of them can exceed 1 in the extreme case. They may both have a plausibility degree of 1, which is actually saying that for the time being, you cannot exclude anything, so you don't know anything. This is representing complete ignorance, so to say. And the smaller these degrees, the more you know, the more you can exclude one of them. You can also think of these plausibility degrees as upper probabilities, if you want. Okay, so here is our proposal of such uncertainty measures. Epistemic and aleatoric uncertainty. So what we assume here is that we have degrees of plausibility for the positive class, given our query instance X, and a plausibility for the negative class, given the query instance X. I will explain on the next slide how these degrees look like. Then we define the amount of epistemic uncertainty by the minimum of the two, and the amount of aleatoric uncertainty by 1 minus the maximum of the two. So this means epistemic uncertainty refers to the case where both the positive and the negative class appear to be plausible. So you don't know very much. In the extreme case, you don't know anything, then this is 1. Yeah? And the amount of aleatoric uncertainty, roughly speaking, corresponds to the degree to which none of the two classes is specifically supported in the sense of appearing specifically plausible. So here, again, briefly, because I don't have the time to go into so much detail here, but briefly, these two degrees of plausibility are defined as follows by this sub-min expression, which you can logically interpret as, the min you can logically interpret as mimicking logical conjunction, and the supremum as an existential quantifier. So you can read this expression here as follows. The plausibility of the positive class for a query instance X is high if there exists a model identified by this theta here, such that the model itself has a high plausibility, and under this model, the positive class is plausible in the sense that its probability is significantly higher than the probability of the negative class. Yeah. So both the plausibility of the model is high, and under this model, the plausibility of the positive class is high. Where the plausibility of the model is defined in terms of what is called the normalized likelihood in the literature, it's simply the likelihood of that model, divided by the likelihood of the maximum likelihood. A model or estimator, so by definition, it means the maximum likelihood. Estimator has the plausibility of 1, and the plausibility of the others is between 0 and 1, proportional to their likelihood. Okay, so what we assume here still, like in standard uncertainty sampling, is that we have a model class, that we have a probabilistic model class, so probabilistic classifiers that assign probabilities to class labels given a query. Okay, and then given this quantification, we can implement this idea of epistemic uncertainty sampling, which is simply uncertainty sampling where always the next instance to be queried is the one which has the highest epistemic Or if you want, you can of course also look at aleatoric uncertainty. So we did some experiments, some first empirical studies comparing this epistemic uncertainty sampling and the aleatoric uncertainty sampling with standard uncertainty sampling. So this is entropy here, the green line, and then also with a so-called creedal active learning method. There is a proposal that comes from the imprecise probabilities people, which work with what is called so-called creedal sets of probability measures, which is closely related actually also to our work. This is why we compared with them. Again, I don't have the time to explain this in detail, but this is the red one here. And also we compared to the standard baseline, which is random sampling. And as you see here, for the Parson window as a base learner, the results actually look as we expect. Yeah, so epistemic uncertainty sampling works quite well, and it works really significantly better than aleatoric uncertainty sampling. And let's say the total uncertainty, the standard entropy, is in between the two most of the time. Yeah, it's in between the two most of the time. Okay, so this is a relatively nice picture, actually confirming our conjecture quite well, that epistemic uncertainty is really the more relevant part of uncertainty. So the same for decision trees as a base learner. Here the picture looks a little bit different. Still epistemic uncertainty sampling works very well, essentially works the best. But the difference to this creedal classifier or active learner is very small. The two perform more or less on a par. And aleatoric uncertainty again doesn't work very well. Here the results for logistic regression as a base learner, they look a little bit different in the sense, and here, by the way, we also compare to this method of Sharma and Bilgic, which are applicable to logistic regression and also to naive Bayes. It's not such a generic method that is applicable to any Bayes learner as our approach, but here it can be applied. Doesn't perform so well. Sometimes yes, sometimes less. But what is important here, the epistemic uncertainty sampling again works relatively well, but the difference to standard uncertainty sampling is relatively small. Sometimes standard uncertainty sampling is also a little bit better. And what we observe in general is that this idea of epistemic uncertainty sampling works less well for model classes that have a strong inductive bias, like logistic regression, where you essentially fit a linear model. And this is understandable simply because for these very restricted model classes, the epistemic uncertainty disappears very quickly. Yeah, you don't need so many data points to have a good idea of where, for example, your decision boundary should be located. Okay, so to conclude, the idea of epistemic uncertainty sampling, as I said, is to apply uncertainty sampling, but with another quantification of uncertainty, yeah, for which we made a proposal. Our first experiments show that this conjecture that actually you should more look at epistemic and less at aleatoric uncertainty in active learning is correct. Yeah, most of the time epistemic uncertainty sampling improves on standard uncertainty sampling, and specifically also on aleatoric uncertainty sampling, yeah, where you look at aleatoric uncertainty. So also our specific approach, our proposal for quantifying epistemic uncertainty seems to work quite well. One advantage is that this is a completely generic approach. You can apply it to any learner you want, although this sub-min computation, the computation of these uncertainty scores, is sometimes computationally difficult, yeah, as you can imagine. Yeah. So this is, yes, what I already said. This distinction between epistemic and aleatoric uncertainty sampling appears to be more useful for learners which have a weaker inductive bias and less useful for learners with a strong bias, yeah, for the reasons I already explained. What we are currently looking at, of course, is to apply this idea to other learning problems going beyond standard binary classification or simple binary classification, multi-class classification, etc. And also, of course, to other active learning strategies, yeah, beyond simple uncertainty sampling, like looking at expected model change and these things. Also, what is interesting is that it might be a good idea to combine, let's say, this quantification of epistemic uncertainty with a quantification of the relevance of a query, because in particular for these non-parametric methods like Poisson windows, nearest neighbor classification, and so on, the epistemic uncertainty is relatively high in regions that are sparsely populated, where you haven't seen many data points so far. So epistemic uncertainty sampling will suggest you to query in these regions, but at the same time, these regions are not so relevant in a sense, because you are not so likely to see new query points again in these regions. Yeah. So in a little bit, in a sense, these two criteria are a little bit in conflict with each other. Yeah. So combining them might be a good idea. All right. So here is a list of references. One maybe I can highlight. This is our first conference paper on this idea of epistemic uncertainty sampling. Currently, we have an extended version of this paper submitted to a journal. It's still under review. All right. So that's all from my side. Thank you very much.
Thank you, Heike, for this very interesting talk. We have a first question about your work of Andreas Zinger. Maybe, Andreas, we can unmute your phone, and in this case, you can raise your question by yourself.
Yeah, thank you very much, Eike, for this excellent talk. I like your topics very much. And so my question would be, would you see that your approach is useful for multimodal explainability or causability? Because I see that your approach has the big advantage that it can produce meaningful and better calibrated measure, and this supports relevance. And I think I regard this relevance, this what is relevant, that is maybe one of the pressing questions which I am constantly challenged.
Yeah, absolutely, Andreas. Thank you very much. That's a very good point that you are raising. And indeed, we are currently working a little bit towards this direction of explainability. I guess you are much more an expert there, but it's perfectly true that in general, this idea of uncertainty quantification and making this distinction between aleatoric and epistemic uncertainty appears to be very important there as well, for various reasons. So one reason is that when you explain something to a user, then normally what you want to achieve is to reduce that user's uncertainty about something. So you have to have a clue about, let's say, the epistemic state of that user and what that user might not yet know. And this is exactly what we would like to quantify with this approach. This is one reason. The other reason is that explainability, I don't know whether you would agree or not, but according to my understanding, explainability has a lot to do also with trust. Yeah,
absolutely. So, yes.
Yeah, and once again here, this distinction I think comes into play. Yeah, if you want to increase the user's, let's say, the user's trust about something, then you have to have a clue about the state of knowledge of that user. And whether it's multimodal or not, both cases, I think, do apply. So here, yes, I do fully agree. Your second point is a little bit more difficult, perhaps. I'm not entirely sure what about causality? So here I have to admit that I did not yet so carefully think about. I could imagine, because once again, causality has a lot to do with uncertainty in general. So I could imagine that the whole ideas do have a role to play here as well, but I'm not yet entirely sure. So I did not look into this in real technical details. I know that probability theory is playing a key role in causality as well. To what extent that could be generalized, referring to other representations of uncertainty, it's a good question, but definitely an interesting one.
Yeah, I meant not only causality in the sense of Judea Pearl. I meant causability, as we have coined it, because causability, we see it as the quality and the checking the quality of explanation. So because this is very important, and this absolutely, and I'm so grateful that you, Eike, said about trust, because this is exactly what causability should enhance. So causability is not incidence, that it is like usability, okay? So causability is the quality of explanations, because explainable AI, to be frank, is rather a technical part. So it is highlighting, for example, what contributed to a certain result. You can visualize it with the heat map, but this still does not support exactly what you said, trust. And I think this trust we should carefully consider, because you are also working in the medical domain, and for me, this is the main point.
Yeah, absolutely. Yes, I fully agree. And coming just very shortly, coming back to this causality, or as you call it, causability, if you interpret it in a slightly broader sense, as you did in your presentation also, then yes, once again, I think I would agree, because it's all eventually about reducing, let's say, reducing the user's uncertainty about something.
Absolutely, yeah.
So, and then you really have to have a reasonable quantification of what that actually means. And this is exactly what we are aiming for. Here we make use of it for active learning, for uncertainty sampling, but this is only one potential application amongst many, I would dare to say. Yeah. So as I said, also during my presentation, this is a topic that we are currently working on, completely independently of such concrete applications like active learning, uncertainty sampling, and so on. Uncertainty in machine learning is a very broad field with a large number of applications, I would say. And yes, thank you very much for pointing out some other directions that might be worth to look at.
Yeah, no, super. Thank you once again for this beautiful talk. I liked it very much. And I will next time when I'm in Paderborn, I will drop by, because I often visit the Heinz-Nixdorf Museum. I'm a big fan and supporter of the Heinz-Nixdorf Museum, and you must be close by.
Oh, absolutely. Yeah, I'm a member of the Heinz-Nixdorf Institute. Absolutely.
Let's have a beer together.
Okay, great. I'm looking forward.
Yes, me too.
Thank you very much, Andre.
Thank you.
Thank you for the answers. We have another question of Listen Young. Which the question is, could you share some intuition?
I think Hugo was first. By the way, I think Hugo was first, right?
I don't see who was bringing his hand.
I think he was the very first, actually.
Who?
Hugo.
Who is Hugo?
Yes,
Hugo Provenza.
Yeah.
Maybe, Daniel, you could give the... Yes. Hugo, you can raise your question.
I think that was a question from a previous presentation, but maybe it only appeared now. I don't know. I'm sorry.
Okay, so you turn to Listen Young for his question.
Okay, but it applies to my talk as well.
Okay. But actually, I cannot read my question anymore. But yes.
No, I mean, this question, I don't know. I mean, but I would say that, I mean, I can quickly read it. So we usually talk about humans supervising machines. But as the machines models get more complex, could we have these machines formulating their doubts about what they do not know, or asking the human expert to acquire more knowledge? How far are we from this? Yeah. So maybe that question was raised before, but as I said, it perfectly applies to my presentation and as well. And what I would say is, yes, I mean, this is exactly, once again, this is exactly what we are aiming for. And I would say that what I have presented here, this application to uncertainty sampling, is one specific instantiation of that. Yeah, so you would like to reduce a certain lack of knowledge, and the machine, in a sense, should be able to express that lack of knowledge. So in other words, the machine should be self-aware to some extent. It should be aware of what it knows and what it doesn't know. Yeah? And this is exactly what we try to quantify, because this is referring to the epistemic state of the machine. Yeah. Yeah? And yeah, I mean, how far we are is a good question. Some first steps have been made, but this is a relatively new topic, I have to say. So we started to work on this. In 2014 or so, yeah. And there we made a first proposal. By the way, it just comes to my mind. Andreas, are you still listening? Andreas Holzinger? Is he still listening?
Actually, yeah, this question, I raised it during the Andreas Holzinger's presentation.
Yeah. Because what just comes to my mind is that our original motivation for coming up with this distinction was really in a medical context. So at that time, we had a collaboration with people from medicine who were interested in applying machine learning to support medical diagnosis. And their uncertainty quantification is really crucial in making this distinction between epistemic aleatoric as well. So our original motivation really comes from the medical domain. I thought Andreas might be interested also in that.
Yes, absolutely.
And yeah.
Yeah, I have also a question also. If you imagine that the train and test distribution are the same, and if we trust that there is effectively an aleatoric and epistemic uncertainty, yeah, maybe I can observe that the convergence of the robustness is faster than using another measure of uncertainty.
Yeah, could
Did you try to have a look on that?
No, not yet. But it's another interesting, oh yeah, it's a good point. It's a good point. No, we did not yet look into this, but it's a good idea. It's a good suggestion. Interesting. I'm not entirely sure, but could be. It's a good point. Okay. Anyway, to just conclude on what I just wanted to say to Hugo. Yeah, this is exactly what we would like to do, and to this end, the machine must really be able to quantify its own uncertainty, and therefore it must be self-aware to some extent. Yeah.
Yeah, like a smaller level of consciousness in a certain sense, that the machine is aware that doesn't know some things, or that it needs more information to do reliable. Yeah, I think that's definitely important.
Yeah. Exactly.
Thank you very much for answering my question.
Okay, good. Double answering. Okay, so I don't know where we are. There is a question by...
Yes, we have one more question.
Yeah.
Listen Wong, if you would like to raise your question.
Hello?
The question, yeah.
Yeah, sorry, there was some technical issues.
So the question of Listen Wong was, could you share some intuition about how can we interpret plausibility?
Mm-hmm. Okay, yeah, good point. So there is not a single unique interpretation of this notion of plausibility, just like, by the way, there is no unique interpretation of probability either. You know that even probability may have different semantics, and you may interpret it in different ways, subjectively, but also from a frequentist point of view, and so on. A little bit the same with plausibility. There are different interpretations. Perhaps the most important one for us is, let's say, plausibility in the sense of upper probability, let's say as an upper bound of probability. A plausibility degree in that sense is, yeah, as I said, an upper bound on probability. So it means that in the very beginning, for example, when you start a learning process or so, and you don't know anything, then all outcomes, for instance, have a plausibility degree of 1, meaning that they are completely plausible. So there is nothing yet that speaks against a certain alternative, yeah? And then you start learning, you make observations and so on, you enrich your knowledge, and then the plausibility of some events will start to decrease, so they become less plausible, yeah? So for example, if you observe a certain outcome almost never, then it's getting less plausible that it will occur next, and so on and so on. And then the plausibilities will reduce. And you may, when you adopt this interpretation as upper probabilities, in the end then converge, let's say, toward a relatively precise knowledge of probabilities. This is one interpretation of plausibility degrees.
Thank you very much. Yeah.
Okay.
Yeah. So, but
Okay. So.
Okay.
Yes. Thank you very much.
You're welcome.
So it remains other question in the Q&A box, but I'm sorry, it's time to switch to the next presentation. So Eike, maybe you can answer in the box in Q&A directly.
Okay, I will try. I will try.
Okay.
Okay.
Thank you again, Eike, for this very interesting talk.
So thank you very much again also for the invitation. It was really a pleasure to attend this nice workshop. Thank you very much. And
okay.
Bye-bye, and see you maybe in the break.
So we are going to now to move to the first regular paper of this second session, which is going to be about LSTM autoencoder based anomaly detection. The presentation is going to be done by Thomas, I think. Yes, Thomas Sabata. So I give the switch to him, and we are going to start by the video. So Daniel, if you can play the video, please.
Hello everyone, my name is Tomáš Sabata and I will talk about the paper Active Learning for LSTM autoencoder based anomaly detection, which we evaluated on electrocardiogram readings. So first, let's start with the motivation. Why is anomaly detection important? In recent days, the amount of generated data is increasing in many domains. We can see it in many fields, such as healthcare, security, meteorology, or Industry 4.0. The main aspect of Industry 4.0 is an automatization, and for that, a huge number of sensoric data, especially time series data, is collected and analyzed. However, a huge amount of data is available, only a small portion of them is annotated. Therefore, unsupervised machine learning techniques are crucial, and anomaly detection is one of them. There are many challenges in anomaly detection. For example, there exist multiple types of anomalies, from sample anomalies, where the sample is anomalous because of its value, to complicated patterned anomalies, where the sample is anomalous if it does not fit into specific pattern. For that, a correct detector has to be selected. Second interesting challenge is setting an anomaly score threshold that is typically used to build a decision boundary that maximizes precision and recall. So, why active learning is helpful in anomaly detection? Anomalies are very rare, therefore knowing which sample is anomalous is much more informative than in comparison with knowing normal sample. The problem is that randomly asking for labels would not be efficient because it will come across anomaly point with only a very low probability, and most of the annotated data will be from the normal class. So having an efficient active learning algorithm can help us to find the correct anomaly score threshold, or even to adjust the decision boundary. This is the motivation why we focus on that. We evaluated our method on electrocardiogram readings, which is the time series data representing a voltage of electrical activity of heart at a given time. With this data, multiple types of abnormalities can be seen by an expert, by a doctor. Below, you can see two pictures comparing one heartbeat, where on the left side, normal ECG can be seen, in comparison to the anomalous ECG on the right side. So let's talk about the approach. First, we will describe how anomaly detection works without the active learning using the LSTM autoencoder. On below, you can see an example of time series. This time series is usually split into windows. These windows can vary in time. They can be various length. They can overlap, and they are fed into the LSTM cells. The LSTM cells usually contains multiple layers with a decreasing number of neurons, and then there is one layer that is copying the hidden state of the last cell and feeding that as input into first LSTM cell on top. Then the goal of the encoder, of the decoder, is to reconstruct the time series, and the reconstruction error is minimized during the training. This reconstruction error is actually used for anomaly detection itself. The point is considered to be anomalous if the reconstruction error is bigger than some threshold. This works very well if the reconstruction error is coming from bimodal distribution, where these two components are very well separated, which is not true all the time. In this picture, we describe our approach that plugs in active learning. First, we start with the unlabeled data set, which is the same with the previous approach, and we train the LSTM autoencoder. Then we set the initial threshold, for example, mean plus 3 standard deviations, and we start with creating labeled data set. So how we do that? We use the threshold, and we count the number of anomalies. On the right side, you can see it here. This is the reconstruction error, so it's increasing, and with the higher reconstruction error, we consider that as anomalies, and we take the same number of points on the left side of the threshold as normal points, and create a labeled data set from that. It's important to mention that we don't use the time series itself. We instead use the encoded features from the code, from the thinnest layer of the autoencoder, which allows us to work with time series that varies in time, and also we trust that the latent space of the autoencoder works quite well for the classifiers. So as the labeled dataset is created, we use resampling algorithms to balance that, because although we are trying to sample anomaly points, it can happen that the dataset will be unbalanced, and much more normal points will be actually in the dataset. So to to mitigate this, we used the resampling algorithms in our experiment. As we have the balanced label dataset, we train a classifier, and as it's standard in active learning, we use some query strategy to find the most informative samples and move them from the unlabeled dataset to the labeled dataset. In our experiment, we use uncertainty sampling, actually the least confident uncertainty sampling. So we use confidences of the classifier to find the most informative samples. So let's describe our experimental setup. So as I said, we are using ECG 5000 dataset. The data are randomly split into training, validation, and testing in ratio 70, 15, and 15. So we have 70% of training data. And we use, as an anomaly detector, we use LSTM altogether with 2 hidden layers, with that's decreasing in the number of neurons. We were experimenting with 11 undersampling and 4 oversampling algorithms that are coming from unbalanced learn Python framework, and with 5 classifiers that are coming from scikit-learn Python framework with logistic regression, decision tree, Gaussian naive Bayes classifier, support vector machines, and k-nearest neighbors classifier. For active learning setup, we use the batch active learning with 30 iterations, where in each iteration we take 10 samples from the unlabeled dataset and label them and put them into a labeled dataset. As I said, we are using the least confident uncertainty sampling. So let's describe the results. In results, you can see 5 charts. In each chart, there is one model. So you can see the model type on top. So as support vector machines, IJCNN, logistic regression, decision tree, and Gaussian naive Bayes. On y-axis, you can see F1 score, and on x-axis, you can see the iterations. You can see there's 3 iterations. The solid lines and with colors are the F1 scores of multiple resamplers, and the colored areas are confidence intervals. And important are also the dashed lines, vertical lines, horizontal lines. The red one is the LSTM performance with the initial threshold chosen. The green one is the LSTM autoencoder performance with perfectly chosen threshold. So this is the best which the LSTM autoencoder, as we start with, is able to achieve. And the blue dashed line is actually our best performance we found during our experiments. So I will go to undersampling because we found there better results. So we achieved the best result with IJCNN with repeated edited nearest neighbor resample. It's an undersampling algorithm. However, we can observe that IJCNN with is actually quite unstable, and we considered SVM to yield much more robust results, and we can see that it actually outperforms the LSTM autoencoder itself, so the unsupervised approach, quite well, and we can see a big potential in this algorithm. So let's sum it up. We experimented with active learning for time series anomaly detection with LSTM autoencoder, and we showed that in our case, the active learning increased the performance of the LSTM autoencoder anomaly detection quite a lot. The truth is that in the state of the art, the LSTM autoencoder, they use the variational LSTM autoencoder, and it has also very good results, even better. So this is our future step. We would like to experiment with variational autoencoder. And also I would like to show our approach on multiple data set, and also focus on different type of anomalies to see the benefits. So I would like to thank you for attention, that you see the presentation, and I would like to ask if you have any questions.
Thank you, Thomas, for this presentation. There is at least one question of Andreas Tesler. So if Daniel, you can give the, yes, you can ask a question, Andreas.
Sure, hi. Yeah, thanks, Thomas, for the talk. I have one question regarding the active learning experiment that you did. I was wondering if you used real human labelers that might potentially induce errors when labeling, or did you use a perfect oracle? So assuming each data set, when suggested, is then being labeled perfectly correct.
Okay, thanks for the question. We have used public available dataset which is already labeled, so I'm not sure if there can be some errors in labels, and we actually used for the experiment labels from the dataset, so we haven't labeled anything and use it as a benchmark.
Okay, thank you.
You're welcome.
Another question? You can also raise your hand to ask your question. No. So one question, Thomas. There is an hyperparameter in your method, which is a threshold. Because you at first it is the beginning of your algorithm, you use a threshold. So what is the influence of this threshold in your result?
Okay, so it's actually a very good question. If you are using the unsupervised anomaly detection, you always need to set some threshold, and as it's unsupervised, it's just some guess you need to rely on. But our approach is actually able to beat some very wrong choosing the threshold, because using the labels you can correct your previously wrong decision about the threshold, and with more and more iterations you can adjust the decision boundary that the threshold set up quite a lot, which actually showed in the results. So as I said during the presentation, if you use the if I use the LSTM autoger and just choose the threshold to get the best test result, so this was the power of the model. As we learned that, we were able to beat that with the classifier on top of the latent layer of the autoencoder. So even if you, so answer is that even if you choose the threshold not so well, the active learning loop can actually correct it in some way.
Okay, thank you.
You're welcome.
So, someone else? Another question? No, but I have another question. So your method is designed for time series, so it should be something like online, and the complexity seems to be high. Or it's possible to manage, or can you give us an idea what is the complexity of your method?
Okay, so it's good to mention that if there are no points adding into dataset, so you have a pool-based active learning scenario, then you can pre-compute the code layers, because you are not adjusting the LSTM autoencoder during the loop, and then the complexity is just additional to the training of the autoencoder. And for the active learning, you just you need to retrain the model So it depends how big batches you are doing and how many iterations, basically. So it really highly depends on this and how computationally expensive is training of the classifier. For example, SVM.
Okay, thank you.
You're welcome.
Someone else? No, I don't see other questions. So thank you again for your presentation.
Thank you.
You are moving to the last presentation for this second session. This is a presentation with the title Towards Landscape Analysis in Adaptive Learning of Surrogate Models. And this is a presentation of Stepnek Pritra. We are going to see the video, and after we are going to have time for the question.
Thanks for watching me today. I'm Stepnek Pritra from the Institute of Computer Science in Prague, and I would like to introduce you our research considering landscape analysis and surrogate models. For the first, I would like to give a spotlight start. We are interested in the black box optimization field, where the values of the optimized function can be gained only through some expensive experiments. To decrease the number of necessary experiments, regression of the already evaluated data is often used. This technique is also called surrogate modeling. As the algorithm explores the optimized function, the function landscape to be fitted changes. Thus, knowledge of the black box function is obtained only gradually during the optimization process. So, if we know all this, which model should we select in each iteration to achieve the best performance of the optimization algorithm? The way we have chosen is to describe the function landscape by a set of features, measure the performance of various models on such function, and after doing this on many data, on many functions, to find some mapping between feature space and model space to be able to select the most convenient model. And if we do all this, we have done some first attempts, and those attempts have shown that we should analyze more deeply the properties of features, of those landscape features, and this work, which I will show you, is the first step in this direction, and here we study feature robustness in computation of those features. Let's start with continuous black box optimization, which we are interested in. As I told you, here the objective function is evaluated only by some experiments or through simulations, and we are interested in the expensive scenario, which means that each experiment is expensive in terms of time or money, so we have only the limited number of function evaluations. In this area, there is a plenty of optimization algorithms. For instance, evolution strategies, and to save these expensive evaluations, we use surrogate models, which are some regression models of the investigated functions. And during the run of each optimization algorithm, there is a situation that algorithm has some previously evaluated points. From these points, it selects the training set, and there is also a prediction set for which we would like to model to do the prediction. And the question is, how should we select the model, the most convenient model for this situation? For this, we have used the scheme where we will first measure a large amount of data, where will be those archives, training sets, and prediction sets. On all of these data, we would measure features, and also we would train models on training sets from these data. Thus, we would assess performance on prediction sets. And after that, when we have features and performance, we'd like to find some mapping which will minimize the error or maximize the performance of the models, and give us the link between features and most convenient models we should use. But when we have tried it, when we have had some first attempts, we have found out that we should analyze features and those connections with surrogate models more deeply. So as the first essential steps, we would like to study feature robustness, because somewhere feature function values are not available, and somewhere features are impossible to compute. So we want to study the situation which is identical in the point of view of the algorithm. So we are in one iteration of the algorithm run. So the data has some distribution generated by the algorithm, and we want to know that if we have different samples from this distribution, the feature will have low variance on these samples. And how we have done it? We have generated the large amount of data. We have used the doubly trained surrogate covariance matrix adaptation evolution strategy, which is surrogate assisted version of the state of the art algorithm for continuous black box optimization. And this algorithm use Gaussian processes, and we have used 8 different kernels to generate those data, and we have run them on the COCOM framework, which is a framework containing 24 noiseless benchmarks, and we have tested it on 5 dimensions and 5 instances, which are some transformations of the input space. So we had these data, which were some original data, some original runs, and we have taken those runs and we have weighted the different distributions from different iterations. So we have taken some previous iterations and some following iterations, and we have done the weighted sum to gain some new distribution for each iteration. And from these distributions, we have generated whole archives, training sets and prediction sets. And from each of these distributions, we have generated 100 samples. And on these samples, we have calculated we have calculated sets of features, which are features from exploratory landscape analysis, which concerns distribution, dispersion, information content, skewness, kurtosis, etc. And all these, I think it was 64 features, we have calculated on the archive, on the training set, and on the prediction set. So we had something about 190 features, and when we had these features, we have calculated in each iteration the variance of the 100 samples. Here you can see the graph for one of the features, which is median distance, where you take the best points in the archive, by meaning the best according to their function values, and versus all points. And the blue lines are the blue line is the variance. Variance is median across the whole data set, and the dashed lines are another intervals. On the x-axis, you can see the number of observations, and the another y-axis is interesting because it shows the percentage of samples which were not able to be computed, and it's the median across the whole data set. And it means that till 75 observations, it is almost impossible to compute this feature. So it gives us important information, and as we can see, this is another feature, which is sensitivity of the information content. And this feature is interesting in that it has large number of infinity values, of minus infinity values, in lower number of observations. Somewhere it also takes some place, but at the start you can see that it is less useful because of the large number of infinity samples. To sum up, we wanted to show you that we study landscape analysis in context of some active learning of surrogate models in the expensive optimization. And the first important step to study this topic is to investigate feature robustness. For future, we would like to continue this research and finish it in the context of studying connections between surrogate models and these landscape features. And also, we would like to investigate another or many selection methods for selection mapping between the model space and the feature space. That's all from me. Thank you for your attention, and feel free to ask questions. Thank you.
Okay, thank you. Thank you for this presentation. Don't hesitate to raise your hand to ask a question. So I'm going to see if somebody would like to ask a question? No, so I have a very simple question maybe. I did not understand what is the link between low variance feature and robust feature. Could you give more indication on that?
You mean difference between low variance features and features with higher variance?
Well, yes. Why do you assume that a low variance feature is going to be robust?
Yeah, no. Low variance features should be better because the sampling was done on the how should I say it? It was because the sampling was done in the same cases. Yeah, because the algorithm was on some place in a search space, and in this and on this place we have done the sampling from the distribution of the algorithm. So the sample was from the same distribution, and it is important for features to have lower variance on these samples, on the samples from this distribution. So because when you are at the same place, you want to get the same values of these features. You don't want to get different numbers for the same cases.
Okay, so but how you impose to be in the same place in your algorithm?
Yeah, that's the main thought of our approach, that we use some kind of meta learning to select the most convenient surrogate model when we are on the same or at similar places. Yeah, so the algorithm moves through the search space, and in each iteration it tries to select the most convenient surrogate model, and our thought is to select the most convenient model according to these landscape features. So the thought is that on the same places, where the landscape is similar or totally same, you want to select the surrogate model which has the lowest error. So the decision is done according to the feature values. So if the feature values would differ on the same places, they would have no use for us, because you would get different values of the same features on the same places, and it would be useless. Is it more clear?
Yes, thank you. Is there another question?
So maybe I would have a question.
Yeah.
Can you hear me? Yes. So yes. When you have the features calculated on the, you said that you calculate them on the training and on the test data, but is there some, let's say, how would you perform? Like I have some I'm a little bit uncertain if that is a good, if that might make it a little bit too, let's say, optimistic, in a sense that how would it, yeah. Let's probably discuss that later.
Okay.
Yeah.
Okay, thank you again for your presentation. I think this is the end of the second session of this workshop.